So in this example, we will try to implement these equations which we have seen, and we will try to calculate the value function for the Markov decision process given here. So here you can see we have four different states. First is state S1, another one is state S2, third one is S3, and fourth one is S4. So in all these four states, we have different actions that we are taking, and these actions are basically denoted by small dots. So and these actions are A1, A2 in state S1, and actions A1, A2 again are taken in state S2. Similarly, in state S3 also A1 and A2 are taken, which is given by these red dots. And after these red dots, we again have the transition from A1 to states S2, from A1 to state S3. Similarly, from A2 to state S4, and from A2 to state S4 if you are coming from here, and from A2 to state S4 again if you are coming from state S3. So basically now we will try to first of all write down the terminologies that we have explained in case of reinforcement learning earlier, that is a policy function as well as the state transition matrix here, and we will try to see where these expressions will be placed. So let us try to see that first. So here I am trying to show you all the possible terminologies that we have discussed earlier, that is the state transition probabilities as well as the policy function pi. So here you can see I have listed down all of them as per where it is present. So if you see here, if you start with state S1, look closely, I am writing v pi S1 here. So this is basically the value function of state S1 following the policy pi. So normally we will calculate the value function v pi of S1 for this state S1, and we will be writing inside this S1 block. Then we have this transition which is going on from state S1, and you are taking action A1 here. So this action A1 is following a specific policy in state S1. So this action A1 follows that specific policy defined by pi. So here you can see for this arrow, the policy pi is given by A1 given S1. So that means in state S1, if you have taken A1, the probability of that is given by pi of A1 S1, which is the policy defined. Then again, the second thing that you will notice over here in this particular arrow is the rewards. So here rewards are defined as a function of state and action. So if you are in state S1 and if you have taken action A1, then the rewards are defined by this definition, and let us call this reward as R1. When you take an action A1, then this reward is when you take an action A1 and in this state S1, let us call that reward as R1. So this is given over here. Once you have taken this action, what happens is this action leads to state S2. So once you end up in state S2, this transition probability which is actually moving you from action A1 to state S2 is actually denoted by a joint distribution given by probability of S2 and R1 given S1 and A1. So this we have already discussed in details in our earlier lecture. So this is basically the environmental dynamics, or you can say transition probability of moving from state S1 to S2, and the reward that you are actually getting from moving from S1 to S2 is actually given by this expression, which is a function of state and the action. Similarly, if you have taken action A2 when you are in state S2, then it is actually given by, then the details of this diagram will change. So here you can see the diagram, here you can see the line segment joining the state and the action will be denoted by this expression, which is pi of A2 comma S given S1, and then the reward is given as S1 comma A2. And similarly, the transition matrix, that is the environmental dynamics denoted by the joint distribution of the state S4 and the reward that you are getting when you are jumping from S1 to S4 is given over here, conditioned on earlier when you had when you were in state S1 and taken action A2. So in this way, you will write down the expressions for the environmental dynamics, the policy that you have defined, as well as the rewards that you are getting in between the state transitions. So for this is I have given you for the state S1. If you do that similar thing for state S2, state S3 and state S4, what you will get is all these expressions that I have written here. So you can do a small exercise yourself and see whether all these terms which I have written over here coincides with the concept that we had discussed earlier or not. So this shows you a complete Markov decision process along with the environmental dynamics and the policy function as well as the reward function indicated on this MDP. So let's move forward and see what we can do next. So now what I am trying to do is to write down these values what are written over here. So what we are saying right now is that the policy, this is basically the policy that we are adopting. And in the policy what we are adopting is that in any state, if you take an action A1, then the probability of that is beta. And if you take an action A2 in any of the state, whether it's S1, S2, S3 or S4, that is not our concern, but the probability of taking an action A2 will be 1 minus beta. And you know that some of the probabilities turn out to be 1, so that's why it is beta, and this one is 1 minus beta for two different actions. So here if you write down these values of beta and 1 minus beta onto the positions where have these policies indicated, all these policies are indicated here. So once you write these values over here, what you get is beta, 1 minus beta, and here also you will have beta and 1 minus beta. So you can write down the corresponding values for this specific policy. So we have actually parameterized this value of beta, and we will vary this beta, and we will see how our policy will change if we change the value of beta. So that we will discuss later on, but right now we are doing it we are putting a parameter beta over here. Next, if you observe, we are also noting down the specific rewards if you are moving from state S1 to S2 or S1 to S4 and so if you are moving from S1 to S2, the reward is given as 0. If you are moving from S1 to S4, the reward we are putting it as 1. Similarly, if you are moving from S2 to S3, the reward is given as 0. And if you are moving from S2 to S4, the reward that is given is equal to 2. And similarly, transitioning from state S3 to S4 gives you a reward of 3 here. Whereas if you continue to remain in state S3, then the reward is given as 1. So this is basically the reward indication, and this is basically putting up the rewards which we have listed down over here. So that's what the values are for the reward. And now the environmental dynamics also is parameterized with the parameter alpha. So we will actually vary alpha, and we will see how this environmental dynamics is affecting the value of the state function. That is for different, that is we will do later, but what we are doing right now is we are putting alpha as the parameter, and we are writing the environmental dynamics probability by using if you are moving from state S1 to S2, you have this probability 1 minus alpha, and if you are if you move from S1 to S4, and if you are taking action A1 is then the environmental dynamics has a probability of alpha. Whereas if you are in state S1 and if you take action A2, then you will end up in state S4 with the probability of 1. So it's an important thing that depending upon the action, the environmental dynamics has different matrices. So that is important. You have to keep this in mind. Here in state S2, if you see, depending upon the action A1 if you are taking, then you are ending up in state S3 or S4. So based on that, your transition probability will have these values. Whereas if you take action A2, in that case, you will end up in state S4, and it's a deterministic transition probability, because here the value is 1, so there is no further movement from here, so the value is given as 1. So please note that this is very important, that is depending upon the action, your environmental dynamics, that is this transition probability will change. So these are the specifications which are listed over here. So let me write down the transition probabilities here depending upon the action A1. Let us say if I actually write the transition probability depending upon the action A1, you can easily write it like this. It's very easy. Here what you are doing is you are actually focusing on action A1 and A1 for all these states, and then you are noting down the transition probabilities that it is making to different states. So for example, if you are in state S1 and if you take action A1, and then from A1, so in that action, if you are moving to the state S2, the probability of that is 1 minus alpha. So that is actually given over here. But if you are in state S1 and you move to state S4 here, with and it is noted down to be value alpha, so that we can check from here. You can see you are in state S1 and then you are moving to S4 by taking action A1. That value is given as alpha. So you can fill in that entry here. And if you see, if you are moving in state from S1 to S3, taking an action A2, its value is given as 0. So you can see here, like there is no action A2 involved in state S1 which can lead to state S3. So that's why its value is 0. So like this, you can fill in all the values, for the transition probability matrix once you have taken action A1 in all these states. Similarly, if you calculate the transition matrix here for all these states, if you have taken action A2, it's given like this. So you can see here it's a deterministic matrix with all the values given as 1. And these all values 1 are coming because you can see that whatever action, if you take action A2 in whatever state, whether you are in S1, S2 or S3, your transition probabilities are all 1. So that's why, sorry, not this one, this one. So that's why you have all the entries given as 1 over here. Now if I want to write the rewards, as you can see, rewards are also a function of A1. So whatever, whether you have taken action A1 or you have taken action A2, rewards also change according to the actions. So what we can do is we can create a matrix like this, which is a one-dimensional column vector, which is, that is having, different states here and the action in the columns. So here you can see if I take action A1 for all different states, its value is given like this. So it's also very easy to see, like if you are in state S3 and if you take action A1, the reward given is to be 1. And this is, you can see from the figure also, that is if you are in state S3 and if you have taken action A1, the reward is given as 1, which is indicated over here. Similarly, if you are taking action A1 here in this state S2, then the reward given is 0. So that's why this value is 0. Similarly, you can write down another matrix where the rewards are given for action A2. So once you write down all these rewards, it will be a one-dimensional column vector which is given like this. And let us check this value, which is basically nothing but the reward when you take action A2 in state S3 is given as 3. So here if you go to the diagram here, now what you see is in state S3, if you take action A2, the reward is given as 3. So that's why it is given over here as 3. So now we have all these 4 matrices with us. Now what we have to do is we have to recall our equation which we had done in the matrix part. If you recall that, what is that exactly? It is basically nothing but given by this expression. If you recall our value of P, it is nothing but this expression here. And what is this expression? It is basically the summation of all the actions, and then you have a probability pi acting onto the state transition matrix that you have for different actions times the V pi. This is basically, if you want, you can expand it like this. Here you have, if you have 2 actions, then it's 2 actions here, so it's given over here. But if you have multiple actions, then you can expand this summation. So here you see, if in case of 2 actions, it is nothing but pi of A1 given as PA1 SS plus pi of A2 given as PA2 SS. And if you see here, what we can do is we can actually, I have written it again here just for notational simplicity. And you can see this transition probability is now dependent upon the policy pi. So that's why we are writing as a superscript pi over here with the state transition probability given as SS prime. And this we already know, we have started out with, the value of this is beta, and for this you already know the value is 1 minus beta. And these transition matrices we have already calculated depending upon the actions. You can see on the top we have these matrices already evaluated, which is given over here. So what we can do is we can actually put in this into the equation which we have written over here. So what we get is this expression. So this expression is basically a parametric expression depending upon the value of beta. So we can see what kind of transition probability it is having based on the different values of beta. We can simulate that in the Google Colab, and we will check it also. That is what kind of policies, like, we can get different policies by varying the beta. So beta can give us various policies, as well as alpha. If we want to vary, then it will help us in changing the dynamics of the environment. So we will not change alpha, because the dynamics of the environment are somewhat, we understand, we assume it to be stationary. But right now we will check the value functions based on the different policies which we can obtain through varying the beta. So this is the equation for p pi of s1. We will keep it as such. Then if you recall, the reward function based on the policy pi will also be given like this for the two states action, for the two actions a1 and a2. And here also, if you see, what we have is, see here, this is the expression for the reward. And here, if you observe, for the two states, you can expand this summation as a1 and a2. So the r pi, the reward based on the policy, can be expanded like this. And here, we have, probability of, the policy for action a1 in any state s is denoted by beta. So beta is known to us, and this is 1 minus beta here. And then these matrices are all, these one-dimensional column vectors are already calculated, and it's given over here like this. So now again we have an expression for r pi. So this is the expression for r pi, this is the expression for p pi. This will be actually beta here. Please note, earlier actually we were discussing it with the value of alpha, but in this example we have taken the probabilities, or you can say the probabilities of the policy as beta now. Earlier when we were explaining the concept, I had taken it as alpha, so I removed it and kept it as beta for this specific example. So now you have r pi, you have p pi with you. So now we can make use of this equation which is given over here, right? So we can make use of with this equation. This you already have calculated, which is this one, which is this expression. And also you have calculated r pi, which is this expression. So now we can fit in these matrices in this equation and calculate the value function for all these states. So what we will do is, we will actually calculate the value function now using Google Colab. We will code this program and see what value function we will get for different values of beta and different values of gamma. So we will try to run this exercise and check and make some interpretations based on that. So let's go to Google Colab and see how to do that. Let us see how we can code this particular Markov decision process in Google Colab. And then once we do that, we will evaluate the value function of all these states. So let us see how we can do that. And please note that here we have 4 states, and with these 4 states, the policy that we are taking is parameterized by beta, which is the policy factor, which we are calling here. And as you can see here, we are calling this as policy factor, so it's 0.5. And then we have alpha, which is the state transition matrix. It's also parameterized by a value of alpha, which will retain it as a constant, and we will not vary it, but you can vary it and play yourself and see what different values of alpha can give you different value functions. But for this particular lab, I am not keeping I'm not varying alpha. So right now we are keeping this alpha as 0.2 here, and the number of states we have are 4, so number of states are 4 here. These are the regular imports which you already know, so there is no point in discussing these, because this is just a simple imports that you need to do for making this program work. So let us see the second portion of it. As you can see here, we have transition matrix based on action a1. So we will define the transition matrix, state transition matrix rather, based on action a1. So this is already discussed here in this particular piece of page. So what we are trying to do is, we are trying to actually now implement this matrix. We are implementing this matrix. So here the code for this is given over here. So you can implement this matrix, which is given over here, like this. Similarly, the state transition matrix based on A2 will be given over here. You can see the way we have implemented it. and we are calling this as P underscore A2 underscore SS, which actually defines the state transition based on action A2. Next, the final transition, which we will have, already that the final transition will be, this particular equation. As you can see here, this is our final transition, and these, specific state transitions which are action based are weighted by the corresponding policies. So that's why we call this particular, state transition matrix as, dependent on policy pi, because it's weighted by these policies. So this final transition matrix, which is over here, we are defining it by P underscore TOT. So this is the final transition matrix that you will get, which is a weighted summation of the policies, which is beta times the state transition performed under action A1 plus 1 minus beta times the state transition performed under action A2. So let us see, if I run this, what we will get. So let me execute this first. Now I will execute this particular piece of code, and then I will try to print these matrices which we have discussed right now. So if I run this, what I will get is, this is the state transition matrix under the action A1, this is the state transition matrix under action A2, and this is the summation of these two matrices weighted by the policy factor given by beta here. So this is P underscore TOT, this one. Now this is just to confirm that the state transition matrices under action A1 and A2 follow the basic probability rule. So what we are trying to do is we are actually summing up the column to ensure that all the columns of a particular row sums to 1. So this is basically trying to evaluate that and see if that is not true, then it will throw an error. If it is true, then it will not do anything. So it's just an error checking piece of code. So right now it has not thrown anything. So this means our state transitions, which are action value based, conforms to this logic. That is, the sum of the columns of the state transition sums up to 1 for a particular row. Similarly, if you see our this thing, we know that we also have rewards based on actions, that is RSA1 and RSA2. So we will be creating these one-dimensional vectors based on the actions. So this particular reward, which is based on action A1, is given over here, which we are calling as reward underscore A1 underscore SS. And we have this reward matrix which is based on action A2, which is defined by reward underscore A2 underscore SS. So let's print these two reward matrices and see what we are getting here. So let me execute this. So you can see these matrices, these one-dimensional vector actually is exactly the same as we have written over here in the explanation part. So these two matrices are actually nothing but this and this respectively. So now again, as discussed earlier, we can also see that our rewards will also be weighted by the policy factors which are given over here, and these rewards are specific to actions and they are weighted by the specific policy. That's why we call this as rewards based on a specific policy pi. So we are doing this summation over here, which is actually implementing this particular equation. So let's run this and see what we will get. So this is the effective reward that we are getting here. So we are actually calculating the total reward, which is weighted by reward underscore A1 and reward underscore A2, and this reward is nothing but this R pi, and its value is given by 0.5, 1, 2 and 0. So this piece of code is same as this is actually calculating the value of the states, which we have also done in our last lectures. So this piece of code is same. I will not go and explain this in detail now. If you want to understand what this is, you can watch my earlier lectures where I have explained this in detail. So here right now I am keeping gamma as 0.99. So let us see what is the value of the states that we are getting here once we use these specific values of the reward and state transition matrices. So let me run this. So what you get is the value of the states given as 1.4, 2.3, 3.3 and 0. So what it means is, like for gamma equal to 0.99, what we are getting is these values. So if I take, let us say, gamma equal to 0.8. So if I take gamma is equal to 0.8, what I get as the answer is 1.12, 1.94, 2.94 and 0. So this is nothing but, these values are given over here. If you see, these values of 1.1, 1.94, 2.9 and 0 are the values which I have noted over here. If you see here, these are the values. So this is the basically expected return that you will get for being in state S1. Its value is 1.1. And being in S2, you are getting an expected return of 1.9, and for S3, you are getting an expected return of 2.9. Similarly, in being in state S4, you are getting an expected return of 0. And if you see this particular state, because this is an ending state, or you can say it's the state where the algorithm ends. So normally, we put the value function of that state as 0. So you can see from this particular observation where you have taken gamma as 0.8 and alpha is 0.2 and beta is 0.5, what you are observing here is, gamma, if you are taking as 0.8, means you are somewhere far sighting your profits. You are having a far sighted policy where you are taking futuristic rewards into consideration. So this is basically a sort of far sighted policy. And what you observe here is that being in state S3 is a profitable state because it is giving you high expected returns. So now if I take a short sightedness type of policy where we will be putting gamma as 0.2. So if I put this value as 0.2, let us say, and if I execute this, what I get is 0.5, 1.1, 2.1 and 0. So if I see this is for the short-sightedness, or you can say you are not giving emphasis to the futuristic rewards, you are actually giving emphasis to the immediate rewards. That is what short-sightedness means. Whereas in far-sightedness, you are giving emphasis to the futuristic rewards also, which will come to you later on. So this is basically that. And here what you see is in the short-sightedness, S1 is 0.5, S2 is 1.17, S3 is 2.17 and S4 is 0. Again here, being in state S3 is profitable. As you can see in the short-sightedness nature also, S3 is the state where agent can remain and earn futuristic rewards. And let us say if I put the value of 0, which means that you are not taking any of the futuristic rewards. What you are interested in is the immediate rewards. So once you run this, what you will get is 0.5120. So that means again, in this situation, being in state S3 is profitable because here you can see the value of that state is 2. So in either of the cases, whether it's a short-sighted approach or a far-sighted approach in terms of the rewards, being in state S3 is always profitable. So now we will try to plot the value function as a function of the probability, that is the beta, which we were discussing. This is basically the beta, which is the policy that we are currently executing. So right now, if you see, all these evaluations which we have done are based on 50-50% policy, where beta is 0.5. This means you are either taking action A1 or action A2 with 50-50% probability. But let us vary this beta and see how this value function will change if we try to take beta from 0 to 1. So if we are using beta equal to 0, means you are actually taking only action A2 and there is no action A1 involved. But if you are taking beta as 1, then that means you are taking action A1 and there is no action A2 involved. And if you are taking any value in between 0 and 1, that means you are taking action A1 and A2 with different probabilities. So let us see how the value function changes with the variation of the beta. So So if you see here, I have taken 1000 samples, and so the beta values are linearly, placed. The points are linearly placed between 0 to 1000. So here we have this, array of 1000 samples, which are equally spaced between 0 and 1. And we are actually, defining the state value here with the array having zeros, where rows are the states and the columns are the samples. So now what we are doing is we are actually, iterating up to various values of beta, and then we are always calculating this p underscore dot, and this total probability is iterative based, because we are running the iteration from, from 1 to the length of the total number of total number of betas variable. So right now we have 1000 samples, so we will be running from 1 to 0 to 1999. So this is basically the iteration that we are doing, and for each iteration you are calculating the total probability, and then we are calculating all these expressions which we have already done for evaluating the value of these states, and then we are storing in a then we are storing the final outcomes into the into the state underscore value underscore alpha. So basically this one stores the values of the state for different values of, actually it should be beta not alpha, because right now you are varying beta not alpha. So let me change all these variables here. So once we have this, let me run this first, and now let me run this. So you can see that you will get the value of these states, this is for state, this is actually for beta equal to 0, you will have value of the state S1 as 0.5, for S2 it is 1, and for S3 it is 2, and for S4 it is always 0. And this is corresponding to beta equal to 1, where you are always taking action A1 and not taking A2 at all. So this is the final values of all these states, and these are all intermediate values for different values of beta. So let us plot some of them and see how our value of the state S1, S2 and S3 and S4 are varying with different values of beta. So let me write this as beta here. So once we execute this particular piece of code, what we get is this variation, and you can see as your beta is varying from 0 to 1, the value function for different states, that is S1, S2, S3 and S4, are varying in this format. And from this it is clearly visible that for any policy, whether it's a 50-50 policy or a policy with beta equal to 1 or 0, being in state S3 is always profitable, because this is giving you the maximum return here as far as the way we have defined our MDP. So this is showing you the variation of the value of state as a function of beta. Now if I want to see the value of the states as a variation of the value of the states as a function of gamma, which is basically telling you whether you are far-sighting the profits or you are having a short-sightedness in terms of the profit. So gamma we are varying for 10 samples running from 0 to 0.99, and you can see when gamma is 0, you are immediately giving emphasis to the immediate reward, whereas if gamma is 0.99, you are giving emphasis to futuristic rewards also, you are taking them also into consideration. So whatever is coming in between that, it's a compromise between 0 and 0.99. So we will see how value of the states is varying with different values of gamma. So this is again same thing. So let me show you various values of gamma. So these are the values of the gamma which we are considering here. So now for these values of gamma, let us actually calculate the policies, and right now I am taking beta as 0.9. So I am not taking a 50-50% policy, I am taking a policy with 90% time action A1 is happening and 10% time action A2 is happening. So in this particular case, we want to see what is the value of the how the state values are changing with the variation in the gamma. So maybe this is not right, we have to write it as gamma, because our state values are changing now with respect to gamma. So let me execute this. This is just to print out a specific value. Now this is gamma here, and let us see this how it varies. It's giving me an error. Let me see what that error is. So actually I was having betas here, so I removed that and kept gammas because uh, I was iterating with respect to beta earlier and not with the, in this case we are iterating with respect to gamma, so I changed it. So in case you are coding yourself, so please change this to gammas. So let us now execute this particular piece of code for beta equal to 0.9. So let me execute this, and then let me execute this now. So if you see here, for beta equal to 0.9, which means 90% of the time we are selecting the action A1 and 10% of the time we are selecting action A2. In that case, you can see how the value of the state is behaving, and you can again see it's increasing, and being in state S3 is always profitable for various values of gamma. Like if you are short sighting in terms of getting interest in immediate rewards, then also being in state S3 is profitable. And again, if you are in the long sightedness approach where you have a value of 1 as gamma, then also in state S3 it's always profitable. So this is basically showing you the trend in the value of the state for a specific policy and for varying the gamma. So this shows, and you can play for different values of policy. Right now, if you keep this policy close to 2, let us say, which is like 20% of the time you are selecting action A1 and 10, and rest of the 80% you are taking selection, you are selecting action A2. In that case, the value states changes in this fashion. But again, in this situation also, being in state S3 is always profitable. So what we observe is for various values of gamma or for various values of policy, the MDP is defined in such a way that being in state S3 is always profitable. But it might be or may not be the case depending upon the problem formulation. So you can vary these hyperparameters as per your wish, and try to see how these value of the states are changing with respect to the policy as well as with respect to the discount factor gamma.